Welcome everyone. अगर तुम अपने PH1003 labs के लिए gear up कर रहे हो, well, consider this session your ultimate survival guide. आज का topic है Computational Physics Module 3 Toolbox. We're going to look at exactly how we use computers to simulate complex classical and quantum systems, process truly massive amounts of data, and basically force machines to solve equations that would literally take us a lifetime to do by hand. So get ready, because we are going to break down the exact tools you'll be using in your hands-on sessions.
Okay, let's dive right into this. Here is a quick look at our agenda. We are covering data types, central tendency, computational errors, the bisection method, and finally, the Newton-Raphson method. Let's get started.
Section 1. Data, sequential and random. So before a computer can actually do any physics, it needs raw materials, right? And in our case, that's numbers. On one side, we have sequential numbers. These have highly predictable patterns. But on the other side, we have random numbers, which by definition lack any pattern at all. But here's the really fascinating part about using computers for this. Machines are built entirely on rigid logic. There's no spontaneity. So to get a quote-unquote random number, computers actually have to use highly complex deterministic algorithms to generate what we call pseudo-random numbers. It behaves exactly like randomness, but it's actually completely calculated behind the scenes.
So, lab में actually ये कैसे करना है? Well, here is a super practical coding jugaad for you. Using Python, you simply import the random module. It's that easy. To get a decimal, you just type random.random. And if you want a whole integer, say between 1 and 10, you just use random.randint. Literally, with just these few lines of code, you can generate thousands of pseudo-random data points to test your physics simulations.
Moving right along to Section 2. Central tendency and dispersion. Okay, so once we've generated these massive data sets, we need a way to find the center just to make sense of it all. We use the classic pillars of central tendency for this: mean, median, and mode. Now, while median and mode give us some really quick structural insights, the absolute most critical anchor for computational physics is going to be the mean.
Now, what's really fascinating here is the sheer elegance of the mathematical formula for the mean. I know. It might look a bit intimidating with that big sigma symbol, but the actual intuition is incredibly simple. You're literally just taking every single element, x1, x2, all the way up to xn, summing them all up and dividing by the total number of elements n. And boom, it gives you the perfect average of your entire data set. But listen, sirf center jana kafi nahi hai. We also absolutely need to know the spread, and that is exactly where dispersion comes in. We have the formulas for sample standard deviation and sample variance. Notice how both of these formulas are basically looking at the difference between each individual data point and the mean. That's the x bar symbol. By squaring these differences and dividing by n-1, we figure out exactly how widely dispersed our physics data is around that center point we just calculated.
Now, if you're looking at those formulas and sweating a bit about calculating them by hand during your lab, please don't panic. This is computational physics, after all. Python's NumPy and SciPy libraries handle all of this heavy math for you. You literally just feed your data into numpy.mean or numpy.median, and the computer runs those complex variance and standard deviation loops in milliseconds. It's an absolute game changer for saving time.
All right, Section 3. Understanding computational errors and the limits of computers.
So relying on computers introduces a pretty massive hurdle. Machines just aren't perfect, so they have to take shortcuts, and that results in what we call approximation errors. Think about a true mathematical function, like an infinite series. A computer obviously doesn't have infinite memory, right? So it just chops off the series and replaces it with a finite sum. It replaces infinitesimally small intervals with finite ones, and it converts wildly variable functions into flat constants just so it can process them. This forced simplification is the root cause of computational error.
Because we know these errors exist, we absolutely have to measure them. Consider this your quick cheat sheet for your exams. There are three main types of errors you're going to need to calculate: absolute, relative, and percentage. Let's quickly break down exactly how they connect to each other.
First up is the absolute error. The formula here is beautifully straightforward. You just take the true, exact value, and you subtract the approximate value that the computer spit out. Those absolute value brackets, that just means we want the raw difference. We don't care if it's positive or negative, we just want to know exactly how far off the machine was.
And this brilliantly illustrates how the next two errors are built directly on top of that absolute error formula. Relative error simply takes that raw absolute error we just found and divides it by the true value, which gives us a ratio. Then the percentage error just takes that relative error ratio and multiplies it by 100. It's this perfect logical flow that lets us tell exactly how inaccurate our physics simulation really is.
Section 4. Root finding using the bisection method.
So how do we actually force computers to solve incredibly complex equations? Well, we find the roots. Mathematically speaking, the value of x that satisfies the equation f of x equals 0 is called the root. It's simply the solution that balances the entire equation out to nothing.
But honestly, if you want to understand it visually, geometrically, a root is just the exact spot where the graph of the function slices through the x-axis. Our main goal in computational physics is to write an algorithm that finds those exact crossing points, no matter how weird or messy the curve is.
Our first approach for this is the bisection method. The core rule here is that we make two guesses, a lower limit called xl and an upper limit called xu. Is method go com garnicalia, the function value at xl and xu must have opposite signs. Basically, one has to be below the axis and one has to be above it. If that's true, it mathematically guarantees that the line crosses the axis somewhere between our two guesses.
Once we've successfully trapped the root between those two guesses, the bisection algorithm calculates the midpoint, xm. It's literally slicing the distance right in half. We check if the root is in the left half or the right half, and then we just slice it again. We repeat this iteration over and over, zooming in tighter and tighter until we finally pin down the exact root. It's a brute force method for sure, but it works perfectly.
And finally, Section 5, the Newton-Raphson Method for fast root finding.
Now, the bisection method is super reliable, but let's be honest, it's a bit slow. And that brings us to a much faster, way more advanced computational jugaad, the Newton-Raphson formula. Instead of using two bounding guesses, it just uses one single guess, xn. But check out the denominator. That's the derivative of the function, f prime of x. This method is incredibly smart because it actually uses the real slope of the curve to point directly toward the root.
By calculating the slope, or the tangent line, at our initial guess, that tangent line basically acts like a slide that shoots us down the curve straight toward the x-axis. We calculate a new point, find the tangent again, and slide down even closer. The algorithm is smart enough to automatically stop iterating when two consecutive x values match perfectly. It is just a wildly fast and elegant way to solve equations computationally.
So, we've covered generating pseudo-random data, calculating statistical centers, and forcing solutions through bisection and tangents, which leaves me with one final thought for you to carry into your labs today. Can computers such a perfect hand? Or are we, as computational physicists, simply mastering the art of managing their totally unavoidable errors? Something to think about. Good luck with module